Hey, hello lovely humans, Jen Foxby here. I'm excited about this video because we're going to do a one episode review of linear algebra, no big deal. So linear algebra is a really useful subject. Was not sure about it when I first took it as a math class, but it pops up all over in physics, in engineering, in coding, data science. Hey, it's very critical to machine learning. So we are going to go focus on linear algebra for just this episode, and then we'll go and come back to machine learning, just like that. So in this episode, we will cover notation for matrices. We will cover matrix multiplication and addition. Addition is pretty straightforward. We will look at the properties of matrix multiplication. We'll do some example problems, and then we'll also very quickly cover the identity matrix, transpose, and inverse. There we go. That was the one I was missing. I was like, there's another I type of matrix. It's important. Okay, cool. If you know about linear algebra, feel free to skip this. But if you're a little bit shaky on it, it's been a while, let's go on this journey together. Okay, so first, when we are talking about linear algebra, we're talking about matrices. Not the movie, classic, but matrix as in a rectangular array of numbers. Now, coding languages are going to have different ways to deal with them. I really like the mathematical notation of matrices. It's what I'm most comfortable with. But anytime I work with them in Python, it's different. But Python is nice because you can just you can make it look how you want, basically. Anyway, okay. So a matrix is going to look something like this. So we have some numbers in here. I'm going to pick numbers from the top of my head, which is always a fun game. Okay, so matrices always have a certain size, which we call dimension. And when we're talking about the dimensions of a matrix, we talk about the number of rows first, and then the number of columns. So in this case, our matrix has 3 rows and 2 columns. So it's a 3 by 2 matrix. You might also sometimes see this notation, where it's a set of, it's a member of real numbers in the 3 by 2 space. If we want to talk about individual elements of a matrix, first of all, we often use capital letters to indicate that a particular thing is a matrix. So a capital letter often means we got a matrix. It's not just one number, it's a set of numbers. It's an array of numbers. But if we want to talk about one specific number in the array, like let's say we want to call out 12, because we have a data set and we're asking some questions and we're like, what was this number in the array? We talk about it, we can call that out with little subscripts, I comma j, where I is the row and j is the column. So in this case, 12 would be 1 comma 1. I guess, well, yeah. And then if we were to talk about 27, it would be a row 1, column 2. If we were to talk about this one, it would be a row 2, column 1, and so on. Okay, let's see, did we want to do vectors first? Yes, we do. Okay, so vectors can also be represented as matrices. They are they have lots of rows, but 1 column. So let's say we have a vector v, and it's represented by this type of matrix. This is a 3 by 1 matrix, or you might just say it's a member of the real space in 3 dimensions. Cool. Okay. Yes. All right. So how do we add matrices together? Fortunately, that's pretty straightforward. If we have two vectors, let's say we have 12, 13, 14, plus 2, 3, 4, we just add each of the elements together. So 12 plus 2 is 14, 13 plus 3 is 16, 14 plus 4 is 18. Yeah, okay. So it is important that we have matrices of the same size to do this. And it works in the same way for subtraction. Dropped my eraser, so we're going to pick it up from the ground. They're like, where are you going? Off camera. Okay. Let's see. Scalar multiplication is also pretty straightforward. And the benefit is that scalar multiplication works for any size matrix. So let's say we have 2 times 4, 10, 1, 11, 3, 9. We just multiply the scalar by each element in our matrix. And this is a 3 by 2 matrix. Okay, so this would give us 2 times 4 is 8, 2 times 10 is 20, 2 times 1 is 2, 2 times 11 is 22, 2 times 3 is 6, and 2 times 9 is 18. So we started with a 3 by 2 matrix and we ended with a 3 by 2 matrix. The same thing goes for addition. The size of the matrices on the equals side is the same as the size of the matrices that we start with. We can also divide by scalars. That is just fine, and it works the exact same way, where you would divide each element in the matrix by the scalar. Okay, so matrix multiplication is a little bit tricky. It is not commutative, but that's fine. Order of operations. If you have multiple operations going on, it just follows standard order of operations. So with matrix multiplication, I'm actually going to stick with the examples here so I don't have to keep coming up with numbers. It's surprisingly hard to think of a random number. Or at least it's hard to think of a lot of random numbers. Okay, so let's say we have a 3 by 2 matrix and we multiply it by a vector. Let's do 1 and 5. Okay, so matrix multiplication works by multiplying the rows of the first matrix with the columns of the second matrix. So what that looks like, I will write it out so we can see how it goes, is we have the rows with the columns. So 1 times 1 plus 3 times 5. And then we do the rows with the columns again. So 4 times 1 plus 0 times 5. And finally, 2 and 1 and 1 and 5. So we have 2 times 1 plus 1 times 5. And then we just do the algebra to get the resulting matrix, which is going to give us 16, 4, and 7. So the important thing to note here, we multiplied a 3 by 2 matrix by a 2 by 1 matrix, and we got a 3 by 1 matrix. So the number of rows stays the same, but now our matrix only has 1 column. Oh, interesting. Kind of sad. Okay, so let's generalize this. If we have a matrix A that is m rows by n columns, and we multiply it by a vector v that is n rows and just one column, we get a new matrix that's a vector because it only has one column. But our new vector has m number of rows and one column. So in a sense, our new vector has inherited properties of both the matrices. Just one column from the vector and m number of rows from our full matrix. Okay, that's all well and dandy, but how do we multiply bigger matrices together? Great question. Do I say great question, audience, or great question, me? I don't know. Okay, so let's say that we have a matrix like this. 1, 3. Actually, I'm going to need some more space for this. Okay, we're going to move on over. Okay, so we have a matrix 1, 3, 2, and 4, 0, 1. This is, what size of a matrix is this? How many rows does it have? 2 rows. How many columns does it have? 3 columns. So it is a 2 by 3 matrix. And we're going to multiply this by, if we do rows and columns, how many rows does our second matrix need to have? It needs to have 3 rows. And how many columns does it need to have if we do rows by columns? Well, this one has 2 rows, so this one needs to have 2 columns. If you're very confused, don't worry, we'll work this out because this can be very tricky. Okay, so we're going to use some colors to help us do this. So again, we go rows by columns. So this first set is going to be 1 times 1 plus 3 times 0 plus 2 times 5. And this second one, so now we need to multiply the first row by the second column. And this is going to be 1 times 3 plus 3 times 1 plus 2 times 2. Uh-oh, I got some holiday colors up in there. That's fine. Okay, and now we move on to the second row because we've multiplied the first row with both columns. So now we go second row, first column. We got orange. Okay, 4 times 1 plus 0 times 0 plus 1 times 5. And finally, we have the second row with the second column. Okay, so 4 times 3 plus 0 times 1 plus 1 times 2. And that's it. And I was very close to running out of space. Okay, so again, just some algebra to work this out. And we get a matrix that is 11, 10, 9, and 14. So our resulting matrix is a 2 by 2 matrix. Huzzah! So in other words, if we have a matrix that is m by n, and we multiply it with another matrix that is, I don't know, a by c, we're going to get a matrix, this is 3 times 2, we're going to get a matrix that is m by b. Okay, so the critical thing here is that the number of columns must match the number of rows here. Okay, so let's do an overview of the properties of matrix multiplication. So we're going to need a lot more board space for that. There are 3 properties in particular. Oh, where did my piece of chalk go? Okay. There are 3 properties in particular that we want to look at. So the first I mentioned very briefly is that matrix multiplication is not commutative. So A times B, or sometimes it's called A cross B, does not equal B cross A, which we kind of saw when we did the 3 by 2 and 2 by 3. We get a totally different matrix on that at the end. But matrix multiplication is associative, which is handy dandy. So if we have A times B times C, it doesn't matter what order we do this, as long as we stick with this order. So for example, if we do A times B first and then multiply that result with C, that gives us the same as if we were to multiply B and C first and then do A. And finally, there's a really fun matrix called the identity matrix. I also think that name is silly, which is often represented with the capital letter I. And this is a special matrix that has 1s along the diagonal and 0s everywhere else. So for example, you might have a 2 by 2 identity matrix that looks like this, a 3 by 3 identity matrix that looks like this, and so on. The identity matrix is always square, meaning it always has n rows with n columns. The number of rows must equal the number of columns. For any matrix A times the identity matrix is commutative, equals I times A, and it just gives us our matrix A back. Maybe that's why it's called the identity matrix, because it identifies our matrix. Oh, math puns, so silly. Okay, note that this is n by n. The identity matrix must have the same number of columns, so n by n, and it does not change the shape, so this is still n by n. Okay, a couple more things: matrix inverse and transpose, and then we're done. All right, so I'm going to give you a sec because maybe you want to take a screenshot of this. These are really, really helpful. Okay. Inverse matrix. Okay, so if A is square, so m by m, then multiplying it by its inverse, which is represented with this little -1, is the same as doing this, and it equals the identity matrix. Hey, what's up? So only square matrices have inverses. So for example, 3, 4, 2, and 16, the inverse of this is 0.4, -0.1, -0.05, and 0.075. So this is A. This is A, -1, and multiplying these together would give us 1, 0, 0, 1. So your question is probably like, how the heck did you get to those weird numbers? There is a formula for finding the inverse of a matrix. Again, has to be a square matrix. You can look that up with your favorite search engine, so I'm not going to go into detail. If you want a resource on that, happy to provide it. Okay, lastly, transpose. Okay, so matrix transpose. Let's say we have a matrix A, which is equal to 1, 2, 0, and 3, 5, 9. The transpose, which is represented with the matrix with a T, capital T, is just taking the rows and flipping them to the columns. So 1, 2, 0, 3, 5, 9. And because I love any excuse to use colors, this becomes the column, and this becomes the column. Okay, yeah, that's it. I'm gonna leave it there for now. Please let me know if you have any questions on any of the linear algebra topics that we've covered. Also happy to do a deep dive into linear algebra. If you're curious, I will probably want to get through machine learning first though, so thank you in advance for your patience. And thank you so much for watching. If you enjoy these videos, feel free to subscribe, to like, that makes me happy when I see that, and share with your friends and family. I enjoy making these and it makes me really happy when they're helpful for other people. Okay, so yay, thank you for joining me on our linear algebra journey, and we'll see you next time. Bye!